Hi, let me show you a different way of multiplying numbers that is not based on the traditional multiplication tables that we all know. So, let me show it to you by using these 4 rectangles that we can arrange like this to make one large square, with a hole in the middle which we are going to fill up with this piece. Great. Now, there is nothing special about the dimensions of these rectangles, by the way. We could have used these other rectangles or any other. Now, the observation that powers the new method of multiplication that we are discussing today is this. The area of the outer square equals the area of the 4 rectangles plus the area of the inner square, pretty obviously. So now we have an equation that we can rearrange by moving the 2 squares to the right side and dividing by 4 to get the area of each rectangle as a function of the outer and the inner squares. Now, let's make this a bit more algebraic by calling the 2 dimensions of the rectangles A and B, so the area is A times B. Then, since the edge length of the outer square is A plus B, its area is A plus B squared. And similarly, the edge length of the inner square is A minus B, so its area is A minus B squared. If you expand the 2 binomials and simplify terms, you will see that the geometry and the algebra naturally agree. And also that we have discovered a convoluted but valid way of multiplying 2 numbers. Take their sum and square it, take their difference and square it, subtract the 2 quantities and divide by 4, and the result is the product. This multiplication technique is called the Babylonian method, so I imagine it's about 3,000 or 4,000 years old. So why would they use this way more convoluted way of multiplying numbers at all? And my guess here is tables. And I don't mean this type of tables, but this kind of tables, of course. Our 10 multiplication tables, 10 rows each. Since Babylonians used base 60, their long multiplications would require 60 tables of 60 entries each, which would have been cumbersome to look up, let alone memorize, of course. However, we do know that Babylonians had tables of square numbers, which they could use to evaluate the a plus b squared and the a minus b squared terms in our multiplication formula. Here I'm using the L of n function to indicate a lookup action into the table of squares at entry n. The advantage of this is that instead of using 60 tables of 60 rows with a total of 3,600 entries, we can now do all of our multiplications with a small table of 60 plus 60 or 120 entries, which is much more manageable. So this Babylonian trick starts looking like something I would want to use in practice, if it wasn't for that pesky division by 4, that is. But luckily we can get rid of it, because why not tabulate square numbers divided by 4 rather than just square numbers? With such a table that has the division embedded in it, our multiplication of the 2 numbers a and b reduces now to something without any divisions and just 2 lookups, 1 addition and 2 subtractions. Alright, so maybe you have noticed that all the even entries in the table contain integers, but that all the odd ones contain a number that ends in 0.25. And that's because an even number n can be expressed as 2k, and the square of that is 4k squared, which can be divided exactly by 4 into k squared. But for an odd entry n, 2k plus 1, the square is 4k squared plus 4k plus 1, which divided by 4 gives an integer and a remainder of 1. Another important thing to note is that if a plus b is even, then so is a minus b. And that if a plus b is odd, so is a minus b. So both lookups in our formula will return either integers, in which case the result is an integer, or both will return an integer plus a quarter, in which case the 2 quarters will cancel out each other and the result will also be an integer. This means that we don't really need to store all these trailing 0.25s. So the final version of our table contains just the integers 0, 0, 1, 2, 4, 6 and so on, which is a sequence that you can find in the online encyclopedia of integer sequences. But what if you don't have the online encyclopedia of integer sequences around to do your lookups? Well, then we could think of pre-generating it by using its definition. But that requires using multiplication to square numbers, which kind of defeats the whole point of using a table in the first place. Luckily, on closer inspection, we see that the differences between consecutive entries in the table are 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on, which seems like a simple enough sequence, assuming the pattern continues like this forever. And it does indeed. Look, the difference between two consecutive entries can be written like this. So when n is an even number, 2k, it takes this form, which reduces to just k. Similarly, for an odd number n of the form 2k plus 1, the difference between terms takes this other form, but it also reduces to just k. And since k is the sequence 0, 0, 1, 1, 2, 2, 3, 3, etc., that means that indeed the entries in our multiplication table can just be easily computed by using this super simple sequence. Okay, so how does all of this work in practice? Well, I quickly gave it a try myself and performed some long multiplications without using the classic multiplication tables that we all know. These were regular long multiplications, except that I processed 2 digits at a time instead of 1 as we normally do, which is equivalent of using base 100. I did this to amortize some of the table lookup time, because I quickly realized that searching on the tables was slowing me down a lot. So this test was really not a fair comparison, because we do have the traditional multiplication tables memorized in our heads, ready for instant lookup. But anyways, it seems to me that in base 10, the gains of switching to the Babylonian method wouldn't be that dramatic. And maybe that's why we don't use the Babylonian method after all. Or do we? Well, in fact, the technique happens to be very useful for many electronic devices that are driven by microprocessors that don't implement any multiplication in hardware, such as the one inside of this Game Boy. That's because a software implementation of a long multiplication runs very slowly, so too many of them could compromise the interactivity and animation rate of the game, for example. Concretely, the software implementation of 8-bit multiplication performs 24 arithmetic operations, but the Babylonian method only needs 3 arithmetic operations and the 2 table lookups, which in an old processor like this is much faster. One downside, of course, is the memory needed to store the lookup table, which for our 8x8-bit multiplication is about 1 kilobyte, or about 2% of the 48 kilobytes of memory in a Game Boy. So thank you, Babylonian mathematicians. Now, there is nothing in the Babylonian method that limits us to the multiplication of integer numbers. Both the geometry and the algebra of the setup work just fine with real numbers as well. Not only that, the method also works with vectors. Look at this. If we take the original formulation and we replace the multiplication of a and b by the dot product of the vectors a and b, and the square of the sum and difference of quantities by the length squared of the sum and difference of vectors, then everything still just works, which I think is mysterious and pretty cool. So with that, I will leave you now and I will see you next time. Oh, but before I forget, there is a pretty mathematical painting that I'm working on that I will be sharing with you soon. So stay tuned. Cheers!